The second section of Chapter 5, 5-2, called Electron Configuration in the Periodic Table, is somewhat review for us because I teach you electron configuration when we talk about, when we take a look at what goes on in the S block, the P block, the D block, and the F block when we talk about electron configuration in the previous chapter, in Chapter 4. Okay, so we're basically going to cover these, 4 objectives here, and we'll move on from there. So, why are the periods as long as they are? Well, if you take a look at this, there are 7 periods, and if you notice, if we do a full configuration, 1s2, 2s2, p6, and so on, we end up with how many boxes? We end up with 7 boxes. So if the answer to the question of how many boxes that you see, there are 7 boxes. 1, 2, 3, 4, 5, 6, and 7. They also correspond to seven periods on the periodic table. How many elements are in the first period? There's 2 elements. Notice that there's 2 electrons to fill those 2 elements. How many elements are in the second period? Notice I'm on the second period here. Here, let me use different color. I'm on the second period here, and there's 8 elements. Notice that there's 8 elements. The third period has 8 elements. There's 8 electrons to fill those 8 elements. The fourth period jumps up to 18 elements. 2 plus 10 plus 6 gives me 18. This is also 18. And then I get up here to 32, and also period 7 can possibly have 32. So there's my 2, 8, 8, 18, 18, 32. I'm sorry, 2, 8, 8, 18, 18, 32, and so on. So that's my periodical law. How many? Let's keep answering these questions. How many periods are there on the periodic table? Of course, we already mentioned that there were 7. So we see that these 2 things correspond to each other. How many elements long is the first period? Well, we already talked about that, and so on and so forth. Okay, so however many elements there are in a period, there are going to be that many electrons that fill that period. So that's what dictates why the periods are as long as they are. Okay, let's take a look at this. The octet rule, when we're talking about electrons, gaining, losing electrons, the octet rule is one of the most important rules, and I put it in here in Chapter 5. The octet rule is possibly the most important rule that dictates chemical law, in my opinion, in chemistry. So what happens is the octet rule is basically the number 8. And the number 8 comes from a full S and a full P sublevel in the highest occupied energy level. So notice with argon right here, I have 1s2, 2s2, 2p6, 3s2, p6. You notice that this has a full octet. It's got a full S and P in the highest occupied energy level. So everything wants to be like an octet. Or since noble gases have the full octet, and again, noble gases are group 18, and since noble gases have this full octet configuration, everything wants to be like these full octets. So having a full octet is a very good, very stable thing for things in nature to have. As a matter of fact, they will, notice the octet rule, elements will lose, gain, or share electrons in order to have this full octet of 8 electrons. I put 18, it's really 8. Okay? All right. So the octet rule is very important. The octet rule occupies about 95% of the known compounds that we have in the CRC book of Handbook of Chemistry and Physics. So lots and lots of materials follow this octet rule. So again, that's gaining, losing, and sharing electrons in order to get to the number of 8, which is a full S and full P of the highest occupied energy level. Now, when you take a look at the S block, okay, this is groups 1, which are the alkali metals, and groups 2. You'll notice that group 1 is very reactive, group 2 is not quite as reactive, and the answer and the question is why is group 1 so reactive? Well, if you'll notice, they have something close to a full octet. So if we take a look at sodium, it's 1s2, 2s2p6, 3s1. Well, I always ask the question, what's the laziest thing in nature to have? Should I gain 7 electrons here? Should I add 7 electrons in the highest occupied energy level? Or should I just lose this one? And the answer is the laziest thing is to just lose an electron. Don't gain 7. When you lose an electron, you'll notice that the highest occupied energy level of 2 has a full octet, 2s2, 2p6. So therefore, sodium wants to lose an electron to have a full octet sitting underneath. And what that does is if I have a full octet now, by losing an electron, then I have an overall positive charge. So sodium actually becomes a +1 charge when it loses an electron. So that's the answer to the question is why is it so reactive? It only has one electron to lose. Group 2 are also quite reactive, not quite as reactive as group 1. But again, the question is why are they so reactive? If we take a look at magnesium, it's 1s2, 2s2p6. There's the octet right here, 3s2. You'll notice, should I gain 6 electrons for a full octet here? Or should I just lose these 2 to have a full octet sitting here? And the answer is, of course, let's lose just the 2, not gain 6. And so therefore I have a full octet here, but since magnesium lost 2 electrons, it must have an overall +2 charge, which we'll learn more about in chapter 6 and 7. Okay? Next. All right, that's just a review of the picture. All right, the P block. These, first thing I want to bring up is that these are groups 13 through 18, so they're on the extreme right side of the periodic table. Just to show you where those things are, here they are. This is the P block. Okay, and I guess it includes helium. And when I have S and the P block together are called the main group elements. So that's important. I will refer to the S and the P block together as the main group elements. Why? We distinguish them from all the other ones because they love to get full octets. Why? It's the S and the P. The S and the P make octets, so I'm going to refer to the main group elements as the S and the P block. All right. Now, the P block has all sorts of stuff in it, almost all nonmetals, all 6 metalloids, some liquid solids and gases, even a couple metals near the bottom. But the thing that I want to concentrate on is group 17, which are the very reactive halogens. And the reason why they're so reactive is because they are so close to an octet. If we take a look at chlorine, it's 1s2, 2s2p6, 3s2p5. You'll notice I am almost at an octet here. So therefore, what chlorine wants to do is instead of losing 7 electrons, 2 plus 5, it would just rather gain 1. So if it'll gain an electron and have a full octet at 3s2p6. So now chlorine just gained an electric charge, a negative electric charge, so therefore it's a -1 ion. And again, we'll move on to that more a little bit later. Okay? All right, the D block. I'm sorry, this is the P block. The elements in the P block will have configurations that will end in the P sublevel. So you notice group 13 ends in P1, group 14 ends in P2, 15 P3, and so on and so forth. Okay, and you could try any one of those things, and you'll notice that whatever column they end in, whatever column they are, they'll end in that configuration. All right, the D block is groups 3 through 12, by far the most enigmatic configurations on the periodic table. Actually, probably D and F are both enigmatic. These are the transition elements or transition metals. They're excellent conductors of heat and electricity. They're less reactive than S block metals for different reasons, and based on their configurations is the answer to that question. Some are also unreactive. They don't easily want to form compounds. We have gold. Silver is actually the most reactive of all the precious metals, and we also have platinum. So we even contain some metals that are extremely reluctant to react. And they have fairly unpredictable configurations. However, what I can do is I can take my S electrons plus my D electrons, and I'll end up with the group number that these things are in. So that's one way that this thing is fairly predictable. Okay, so that's the D block elements, which are right here. Okay. Last, we have the F block. Not going to talk too much about this. They actually fall between groups 3 and 4. And these are mostly lab-generated elements. And the F block elements are down here. Okay? Just a little bit of review there. So again, we know how to read the periodic table when we do this stuff. We know these rules already, but essentially you're responsible for being able to do electron configuration and also reading the periodic table. Okay? That about sums section 2 up.